Alrighty, this is Ms. Martinez, and I'm going to be speaking in this video about inverse relations and functions. So let's get started. The objectives for this lesson are to find the inverse of a relation, determine its domain and range, and then state whether it is a function. Then we're going to look to determine whether a function is one-to-one, and we'll use function composition to determine whether two functions are inverses of one another. So let's get started with the idea of an inverse. If you have a relation R, we'll call the relation R. Relations are just ordered pairs. So say in this relation you have the ordered pair AB. Then its inverse relation, which you would denote R, and then in the exponent a little -1. That's how you write the inverse of R. It would contain the ordered pair BA. So what we've done here is we have flip-flopped, or we have switched the domain and range. A was in the domain, now it is in the range, it's in the y values now. B was your y value in R, in the original, but now it is your x value. That is, by definition, what an inverse relation is. Visually, say this is our relation R. You see the domain, it's that green circle, and it's paired with items in the range. The inverse would be literally taking the range, making it the domain, and mapping it to what was once the domain. So all we did was just switch what was originally the range, it became domain, and the domain of the inverse, the range of the inverse, that green circle, well, we know that because it was the domain of the original. Let's work through an example together. Here we are given a relation Q, and there are four ordered pairs there, and they describe the vertices of a quadrilateral, of a four-sided figure. We want to find the inverse of Q and then graph both Q and its inverse. So the inverse of a relation, if you look back, it is just the switching of those values of x and y. So it would be 1, 2, 1, 4, 2, 6, and 4, 5. That would be the inverse. And now we're going to plot these, and I tried to color coordinated it so you can see the relation versus the inverse. If you just plot those points, you see that there's 4 blue points for the original relation, and that does yield a four-sided figure. And then the red points represent its inverse. And notice that they are reflections of each other. They're reflections of each other across a very unique line. It's the line y equals x. And this will be true for every relation and its inverse. They will always reflect each other like this. So I'll say that again because it's really, really important. Relations and their inverses will be reflections of one another across the line y equals x. What if we have a function and we're asked to find the rule for its inverse? Well, we're still going to use the same idea here of switching the domain and range. And these will be the steps that you take. The first step is if it's written in function notation like we have here, you'll want to rewrite it using x and y. So that function is really y equals 2x plus 4. Then switch the x and y variables. So if we switch them, now we're talking about the inverse. So the inverse of our function f is x equals 2y plus 4. All I did there was switch x and y. I didn't change anything else, just switch the variables. Now, step 3, the final step, is to solve the inverse for y. To do that, you would want to subtract 4 from each side. And then to get y all by itself, you'll divide by 2. If I simplify that, I'll have y equals 1/2 x minus 2. That is the inverse of my function f. Let's do another. Now we're working with the function g, and it is a quadratic function. So we begin by expressing it in terms of x and y. So instead of the g of x is really y equals x squared minus 2. Then we're going to switch the we're going to switch the x and y variables. So the inverse of g would be sorry about that, would be x equals y squared minus 2. And then you would solve for y. The first thing you'd want to do is add 2 to each side. And then to get rid of the square, you would need to perform the opposite operation of squaring, which is taking the square root. And we have to denote that it could be the positive or negative root. That's what that little plus minus is outside of there, outside of the radical. Because we're not sure what y was. So that's really important. This is a great example. You'll need to refer back to it pretty frequently during this lesson. All right, now let's talk a little bit about this. There's another test that we're going to study in this section. If a horizontal line can be drawn through the function f, and it touches only one point at a time, then its inverse, which would be called f, and then to the -1, you would read that as just f inverse, will be a function. So we've studied the vertical line test, and vertical line tests tell us that the function is a function, that the graph is a function. The horizontal line test, when you use it on an original function, it will tell you if that function's inverse would be considered a function as well. Then, if you checked the original function with the vertical line test and it was a function, and then you checked that function f horizontally and it passes and its inverse is a function, that function is considered a one-to-one function because its original and its inverse are both classified as functions. They both graphically pass those tests. If a relation and its inverse are functions, this should happen. And you all, when you were working in the previous section, you came across this kind of problem where you took the composition of two functions and the output was x, no matter the order. you all did this. This was the problem that was on the podium. You plugged the g function into the f function and the output was x. And then you did similarly, just the opposite order, and the output was x. That was because those two functions were inverses of each other. So let me show you with an illustration. Let's say that you have the composition here. We're working with f inverse of f at 10. That's really just f inverse of f at 10. I've just rewritten that. That would look like this. You'd be plugging 10 into your f function, and if it was 2x plus 4, that would give you 24. 24 would be the input for the f inverse function, and when you plug that in, half of 24 is 12, minus 2 is 10. Notice you got the same output that you put in originally. You plugged in 10 to begin with, and you got out 10. That is because these two functions are inverses of each other. And if you did this just the other way around, where it was the inverse that was inside of the function, the same thing happens. Plug 10 into the inverse function. You'd get out of that 3. 3 would then be plugged into the f function, and the output there is 10. This is happening because these functions are inverses of one another. And this is how you check that two functions are inverses. If someone asked, are these two functions inverses? You would do this composition the two ways, and if you got the output that was your input both times, they would in fact be inverses of one another. All right.